the end behavior of a function describes how a function blank as it moves infinitely to the right or left. At how a function changes as it moves infinitely to the right or left. In other words, the end behavior is what happens to the values of y as x increases or decreases without bound. Okay, so the actual idea of end behavior is going to be pretty simple and pretty easy to tell what's going on. What's going to be new is some notation and some notation and some like language that we have not really seen. You do end behavior some in Math 3. And typically in Math 3, we say things like, as x approaches infinity, f of x approaches 2, or f of x approaches negative infinity, or whatever we have there, right? That's typically the phrasing that we use for end behavior. In AP Precal, we're introducing limit notation. So I don't believe you've seen this type of notation right here before. Anybody seen this? Okay, so this limits is actually my whole first unit in calculus. So I kind of like that they go ahead and introduce this notation here. Now, there's a lot more that we do with limits in calculus, so we're not learning like all of calculus here. But this is introducing how we can use this notation to talk about what's happening at the end of the graphs. So, we will talk about the left side of the graph and the right side of the graph. For limit notation, we will have the limits, this is called the limit, as x approaches negative infinity of f of x, or whatever function that you are dealing with here, g of x, h of x. Sometimes you might have the actual equation right there. But we're doing limit as x approaches infinity. So, for polynomials, our answer is always positive infinity or negative infinity, because polynomials always go off to the ends. That doesn't have to be the case for all types of graphs. So as we introduce more types of graphs, particularly I'm thinking logs and exponentials, which we will do next, I think. It's not, if it's not 1b, it's 2a. I can't remember which one it falls on. We will actually see like limits that are numbers, because we have like horizontal asymptotes and vertical asymptotes that we'll look at. But for these problems, we're just talking about the ends of the graph going up or down. So when we see this x approaches negative infinity, that tells us that we're talking about the left side of the graph, because on this graph, on that x-axis, this side over here is negative infinity. So we're talking, if you start in the middle and you go out towards negative infinity on your x-axis, what is happening to the y values of the graph? That's what this means. So, so when we see limit as x approaches negative infinity of f of x, that is our left side. We also may see this worded as the x values decrease without bound. Without bound, meaning that it never stops right there, right? I have had students before that talk without bound constantly. Won't be quiet. Not any of you guys, because we may almost have the opposite problem in here, is that you guys are very, very quiet. So as the x values decrease without bound, just means the same thing. X values are going further and further and further and further negative. Then the y values of f of x do this or that, right? For the right side of the graph, notice we've got that same limit notation. It looks almost identical. What's the only difference between left side behavior and right side behavior? We've got positive infinity right here. X is approaching positive infinity. So that means right side of the graph, because x goes to positive infinity over here on the right side of the x-axis, right? And then instead of saying that x values decrease without bound, we would say x values increase without bound, if we're talking about the right side of the graph. So, for this, it's really in working with the notation. The idea is pretty simple. If you think of this, what you're trying to do is thinking, like, what happens out at the very end of this graph. And for polynomials, it is always going to be that they go up or down, right? So, like, if you try to make yourself this graph right here, then this side goes up, this side goes down. So my left side approaches positive infinity, up is positive infinity, right? My right side approaches negative infinity. So to write this out verbally for the left, it is appropriate. In Math 3, we said as x approaches negative infinity. That's fine. In fact, I think I'm going to write both of these things down here. As x approaches negative infinity, f of x approaches in this case, on the left side, that left side of the graph is going up, so approaches positive infinity. That's how we wrote it in Math 3. And this is still correct. It is fine to write your answer like this. This is still correct. However, if you see this worded on AP stuff, it's not the phrasing that they like to use the most. So we're going to try to write these in the phrasing that AP likes. It's not going to matter if you are having to write in an answer. In fact, a lot of times they're going to be asking for the limit notation anyway. But it will help us, like if we get a multiple choice question about this, or if we get a question that maybe it's free response but it's written out in words, it'll help us understand what it's asking for. So instead of saying as x approaches negative infinity, AP likes to say as x decreases without bound. F of x, or maybe even the y values of f of x. In this case, if we're going up, then that is increasing without bound. So f of x increases. So you can kind of like mirror that you're like used to writing. As x approaches negative infinity, that's as x decreases without bound. And then whenever I have f of x approaches positive infinity, that's f of x increases without bound. If we had a negative infinity there, it'd be decrease without bound, right? So if you're talking about positive infinity, increase without bound. Negative infinity decreases without bound. So we're going to kind of try to stick to that language just for practice with it here, but it doesn't mean that what you did in Math 3 was incorrect. It's just another way to throw in there for that. Now, limit behavior. When you're doing limit behavior, you are going to do limit, L-I-M. Underneath the limit, you're going to put x approaches. We are on the left side, which is where x is approaching negative infinity. You want to make sure that you put f of x right here, or whatever function you're dealing with. It could be g of x, it could be h of x, whatever. You want to put that there. And then you're going to say that equals, in this case, because on the left side our graph is going up forever, that is positive infinity. I do love limit notation because it sort of condenses it. You don't have to write it out in words. Mathematicians are constantly looking for a way that we can use symbols and things to like condense everything down instead of having to write a bunch of words out, right? Constantly avoiding words. So I do like limit notation. If we want to write a right behavior verbally, we would say for the right side, it's always going to be as x increases without bound. F of x. In this case, on the right side, my graph is going down. So f of x decreases without bound. And so that limit notation looks like this. Limit as x approaches positive infinity of f of x equals negative infinity. So that x approaches just tells you whether you're going to the right or to the left. The answer, whatever the limit equals there at the end, that is whether or not your function goes up to positive infinity or down to negative infinity. Okay, make sense? Try the other one on your own. Try that one on your own. Okay, looks pretty good as I'm walking around. I think we're doing pretty good. I was specifically looking for one thing that I did not see anybody doing, so that's good. Here's what we should have. Left is as x decreases without bound, f of x increases without bound. There's your limit notation there. Limit as x approaches negative infinity of f of x equals infinity. For right behavior verbally, you've got as x increases without bound, f of x increases without bound, and the limit as x approaches infinity of f of x equals infinity. So I think it looked great as I was walking around. There is one thing that I want to warn you strongly about. Nobody did it as I was looking. I was specifically looking for one thing. Let's look at the next. Oh well, hold on. Well, let me just write it down here. Here is what I want to warn you about. I'm gonna warn you right now. And then some of you are still going to do it, possibly, at some point. When you are taking the limit of a function, you have to have a function right here, right? There has to be something there. But what I see kids start doing, especially as we've done a lot of these problems, is they just start doing something like this. Limit as x approaches infinity equals infinity. Right? My calculus class does it awful whenever we get there. This is not a mathematical term. Don't go tell your PhD professors in college about naked limits. But I call these naked limits. Because you were taking the limit of nothing, there's nothing there, right? So I call these naked limits, and if you do this on a free response part of the test, I'm going to draw this fellow right here who is shocked that you have put a naked limit on your paper right here. Probably the first test, I'm probably not going to count off points if you have a naked limit, because I do understand you probably knew what you were talking about there. Your notation is not great. But after the first test, I usually start taking off at least like a little bit for those, because this is not mathematically correct. You must have right here the function. So watch out for that. Usually, I always warn students, but then usually you sort of get comfortable and start going fast, and you do it, and you don't even think of it. Honestly, I do it every once in a while, and then I feel ashamed of what I've done. So watch out for that. It may happen to you. These next two, I want you to sketch me a polynomial function. So a polynomial function must be continuous, right? A polynomial function with the following end behaviors, okay? I want you to do this before we look at it, because there's lots of different correct answers that you could have for this. So try these on your own. Vanna, forgot to cut it back on. Here's the answers to the others. There we go. All right, so limit as x approaches negative infinity of, this time, make sure you use a g of x here, because this function is named g of x. And then we would say negative infinity, but the limit as x approaches positive infinity of g of x would equal positive infinity. Everybody good here? Now they asked us here on example 5 to use a graphing calculator to determine the end behavior. But do we need a graphing calculator for A? We do not. So let's not waste our time typing it in, because I can see that the right side is going to go up, and I have an even degree. The left side also goes up as well, right? So I'm going to write this in limit notation. Limit as x approaches negative infinity of f of x is going to equal positive infinity. And the limit as x approaches positive infinity of f of x is also going to equal positive infinity. This is also something you might see like on ACT. It's not going to have limit notation if you see it on ACT, but you may see as x approaches and negative infinity, f of x approaches positive infinity, that sort of stuff. So there's a super fast ACT question, right? If you see that, because typing it in the Desmos, yes, you'll know it for sure, but like it takes time, right? You can do this quickly this way. Now, B is a rational function, and we probably for sure are not going to be doing well enough with those to be able to tell them without graphing. So that one we'll type in, and I'll just type it in for us here. So we got g of x equals 2x minus 3 over x plus 1. Now, we got some weird things happening on this one. I think he's just throwing this in here just for a little extra. What just happened to my last night's homework. Where'd my... Oh, somehow I put it up here. Okay, so he's just throwing in sort of like a little bonus right here, because is this a polynomial function? This is not, because polynomials only have like x raised to powers. They don't have fractions, things in the denominator. This is a rational function. This is like a preview of coming attraction, so I think he's just throwing it in here to make sure you know we don't always get positive or negative infinity, right? So if I look at this graph right here, my limit as x approaches negative infinity of g of x here, does it look like that graph right there decreases without bound forever? Does that graph go down to negative infinity? It does look like it decreases forever, but it looks like a horizontal line, right? What's happening on that graph? What have we got on that graph? What? We got an asymptote on that graph, a horizontal asymptote, right? So what's happening is that graph is getting closer and closer and closer and closer and closer to that line, which appears to be, I'm going to type it in, y equals 2. Oh, not 21, 2. And it looks... Oh yeah, this looks like an asymptote. They look like they touch. They look like they're the same line, right? But if you click on it, they're not touching. And if you zoom in, oh, they're not actually touching, right? And so that's like, that line's just getting closer and closer and closer. So in this case, you can't have a number. That, on the left side, your y values are just getting closer and closer and closer to 2. You won't see it on polynomials, just on rational or different types of functions that are not polynomials. And then if I do the same thing for the right side, limit as x approaches positive infinity of g of x, then we can see, oh, the graph approaches that same line, approaches y equals 2 on that other side, so we would get 2 for that. So he's just throwing this in here for us to see that it doesn't have to be positive or negative infinity. If I graph h of x equals negative 10 over x squared, then I got this weird stuff happening in the middle, but I don't care about the middle, right? I could use some limit notation for that, but we're not there yet. We're not going to talk about that. We're talking about the ends of the graph, like what happens as I go over here, closer and closer and closer to negative infinity. So my limit as x approaches negative infinity of h of x, what does it look like it equals here? 0. Right, that's the x-axis is where our y coordinate is 0. And it appears that that same thing happens on the right side. So the limit as x approaches infinity of h of x also equals 0 on the right side. So for polynomials, you should always get positive infinity or negative infinity as your answers for your end behavior. But there are other ways, right? And you may see some sprinkled in where it's calculator active, and you could graph that. I would not ask you at this point to tell me end behavior for these without a calculator. A day is coming where I may, but right now it would have a calculator. Quiz tomorrow does not have a calculator on it either. We really haven't done much with the calculator where you would need it. So no calculator on tomorrow's quiz either. So we are done. Look at us. I have posted here, we're on day 15. There is an optional quiz review. This really was supposed to get dragged down here. This is not extra credit. It is just optional if you want to look at it. We're probably going to have a little extra time at the end of class today because I do not think it will take you 30 minutes to do the worksheet that I've got for you. I did not print it because it's not required, and I didn't want to waste a bunch of paper for people that were not going to do it. But this is good stuff to look at to review for your quiz tomorrow. So there is a blank copy and also the key. What I would suggest if you get your worksheet done, or well, actually, what I require. If you get your in class, you need to be working on math the whole time, unless you've got the worksheet and this done. But this is not required for homework. Just jot your answers down on notebook paper. The quiz, I think, does have 10 questions instead of 8, but this just highlights a few of the things that I think might be something that you need to look at for the quiz tomorrow. And then you can check that with the key for that. So